Good morning. So many of you were at the Q&A last night. I think you enjoyed it, right? And the smaller room worked out okay. So we're planning for the tutorial, which starts at 4, to hold a tutorial on lattice field theory, Q&A on lattice field theory, also in the same room with the lecturers. So similar to what we had last night. Okay, and now Mithat will give us his third lecture.
Okay, thank you very much. Yeah, after yesterday's discussion, I decided to make the lecture a bit more pedagogical and a bit slower. And I also wrote some notes so that I can move forward in a more organized manner. So today we will discuss semi-classics in 2-hoofed flux background. Both of these words are known now for over 4 decades. Maybe originally it was 2-hoofed's intention to construct something like that. When he was constructing this 2-hoofed flux background, he was actually hoping to get some spectral data about QCD. That didn't work out quite well, but the paper is a classic. It's a fascinating paper, actually multiple of papers in which he introduced 2-hoofed flux and related ideas. So the title is Yang-Mills on, let me call it M2 times T2. T2 is a 2 torus. Okay, M2 can be anything. In particular, it can be R2 most of the time. It will be with or without flux, with or without 2-hoofed flux. Actually, you will see that even the introduction of the 2-hoofed flux immediately does something interesting on the theory on R2 times T2. And as I said, I promised I will be slower, so we can start with the Yang-Mills section. 1 over G square, there is a kinetic term, trace F wedge star F plus I theta over 8 pi square. This is the topological term, integral F wedge F. This part is, of course, the instanton number. And this thing here is called theta angle, and the instanton number is integer valued. Okay, let me state, I already stated the symmetries. The theory on, the theory always has, on R4 has a Zn one-form symmetry, but if you consider it on R2 times T2, this one-form symmetry decomposes to this is 4D. It decomposes to two-dimensional one-form symmetry. And I will actually give a precise definition because we realized yesterday in Q&A that we didn't give a precise definition of the one-form symmetry and its generator. And it will come out naturally when we do the construction. And there is 0 form parts, Zn0 and Zn0. And these parts are acting on the Polyakov loops. Let me call Polyakov loops. Let me call compactified direction 3rd and 4th directions. Actually, let me do as follows. Is this a board? Yeah. Or why don't you come down? That's also yours. So this torus, I will call the compactified direction X3 and X4, and consider the Polyakov loop around this direction the name I will use is P3 and P4. In the SUN gauge theory, with no 2-Hooft flux turned on, for example, P3 is path ordered exponential integral of A3, and similarly, okay? When we do this compactification and go to small T2 limit, F3-4 component behaves like a potential. F3-4 for the lowest mode, 0 mode, this becomes something like A3, A4 commutator, okay? And F3-4 square, trace F3-4 square becomes trace distinct square. This is just regular potential. You can view A3 and A4 as adjoint scalar fields, the algebra valued scalar fields. And the minimum of this potential is, of course, at what we would call F3-4 equal to 0. This is called flat connections. And along which this, at the minimum, mean P3 and P4 must commute, because A3 and A4 commutes, and P3 and P4 must commute, okay? So that means they are simultaneously diagonalizable, okay? They are simultaneously diagonalizable. Okay. What can I write? So essentially P3 is equal to exponential I, let me call it alpha 1 through I alpha n, some set of angles. And so for P4, let me call it I beta 1, I beta n. Not that important anyways. This is classical story. Classically, there is a flat direction. But of course, quantum mechanically, it is different. At any rate, flat directions are always subtle in 2 dimensions. And you can calculate the one loop potential, and one loop potential is not very surprising. It is just generalization of what I mentioned in the previous lecture, you know, generalization of the Gross-Pizarski calculation. It is minus 2 over pi square L to the 4, sum over n3 and 4, 1 over n3 square plus n4 square squared, trace omega 3, omega 4, n3, n4 modulus square. The most important thing about this potential is actually this sign up front. It tells you that both of these Polyakov loops are tachyonic. So that means that the symmetries that I wrote down up there, Z and 0, product of 2 Z and zeros. So the implication of this, that Zn1 times Zn0 times Zn0 will be broken down to Zn1. This part will be completely broken. At low energy, you reduce to pure Yang-Mills theory in 2 dimensions. It's a confining theory. This is the reason that this one-form part is unbroken. So in essence, what happens in this theory, when you compactify it on R2 times T2, this is R4. This is the picture I made earlier. Let's say this is symmetric torus. As you go to small torus, there is a phase transition in which both of these symmetries are broken. This is not what we want. Yeah. Of course. Pull it down. Yeah. I use different symbols. Oh, okay. Yes. Did I call? Where did I? Oh gosh, I am terrible. Okay. This is the reason I should prepare notes, because I cannot stay completely constant. Yeah, P3, P4. Yeah. Okay. Please interrupt anytime you want. But we want, when you turn on 't Hooft flux, something extremely interesting happens. And let me describe to you what it means to turn on a 't Hooft flux. Okay. First of all, I can describe it to you the way 't Hooft did. Okay. So, okay. Good. So it is from 't Hooft's perspective, turning on a discrete 't Hooft flux is using twisted boundary conditions by using transition functions. So if you consider the theory on the torus, let's say this is the theory on the torus, what you do is you define some field here, okay, or let's say at the corner, it doesn't, or somewhere here, okay. You define a transition function, you define the field here via the transition function, and there via the transition function, and you demand you can reach to this corner by using either this path or that path, okay? And you demand that the field here be independent of what path you have taken. So you demand the consistency of the field there. So let me call x3 x to lessen the clutter, x4 y for a moment, okay? So let's say we look to gauge field A, X, and this is Lx, this is Ly. Let me write down this twisted boundary condition by using transition functions. I am looking to field here at any value, actually here, okay? Let me look for generic adjoint valued field. This is some adjoint matter, because it requires more slightly more writing for gauge field, some adjoint matter. So this will be equal, I need to use a transition function, Gx, the transition function, dagger y, phi, x equals 0, y, gx, y. And similarly, I need to write phi x comma y equal ly is equal to transition functions now in the y direction, which are functions of x variable, phi x comma y equals 0, and gy of x. So I define the field here, the field there via these transition functions. Now you can reach to this corner via these two paths. If you reach via this path here, you, okay, let me go something more explicit. So at this corner, you end up with the following situation. Schematically, you end up with gx dagger, gy dagger, phi, gy, gx, or either that or the other possibility is gy dagger, gx dagger, phi, gx, gy, these transition functions. So they almost agree. Actually, if these things if you have the following condition, if these things agree, if you have the following gx ly and gy 0 is equal to exponential 2 pi I over n, little n. This is the important thing here because there is the gauge invariant information here. Lx gx 0, okay. If these transition functions differ only by a phase, the field here does not have any jump depending on the path you have taken. It is consistent. This is the way 't Hooft constructed 't Hooft flux. And this n here is called 't Hooft flux. I will also tell you the more modern reincarnation of it, more modern meaning. Yeah.
Are these transition functions Wilson like?
No, they are really, they are, okay. They are really the functions that connect one patch to the next. So they are actually useful in constructing bundles, okay? So, but for now, you just view them as transition functions which provide you some twisted boundary condition. But let me not go more detailed than that. But the point, actually, these things, they will even, the existence of 't Hooft flux will even modify the definition of the Polyakov loop. But it will become momentarily more clear, okay? But at this stage, they are just transition functions. They actually, like Polyakov loop, they also transform under the gauge transformations also act on them. In this equation, there is only one gauge invariant information, physical information. It is this thing there. And N. So this is the flux that I put on the on this torus on the 3-4 direction. Okay. Now, actually, you can use a gauge transformation in which the transition functions are independent of coordinates. Okay. And this brings us something that Nati mentioned in his class. This is gx, gy is equal to exponential 2 pi I over n little n gy gx. This is sometimes called Heisenberg algebra. This is sometimes called 't Hooft algebra. It has multiple names, but you are very familiar with it from the context of quantum mechanics. If you, let me put something very intuitive, you can realize this thing in terms of clock and shift matrices. If you consider particles on a discrete lattice, clock matrix is like position. The eigenvalues of the clock matrix are these positions. So clock is 1 omega squared omega to n minus 1. You know, acting on these things. And shift is discrete translation. Shift is on the diagonal, it is 0. On the off diagonal, 1, 1, 1, all the way 1 here. These are the discrete translations, and the two satisfies this beautiful algebra. Okay, and it gives you useful information about the yeah. This has the okay. Let me push this up. Say that I.
While you're pushing those around.
Of course. Yeah, gauge fields or any other field in different patches on the torus.
That's why I say the torus has both flux and flow.
On that, yeah, on that 3-4 cycle, it will have 2 flux n. In principle, okay, so maybe, okay, let me go one step forward, then I can come backwards. So you can actually, for torus, if you take a 4-dimensional torus, okay, how many phases, how many cycles does it have? 6 of them, right? Yeah, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Okay, 6. And you can define these integers as 2 fluxes passing through mu nu cycles of the torus. Okay, this is this. So there are these, and each one of them is valued, as you can see, it is the n valued, is valued from 1 to n. So there are these possibility of n to the 6 numbers. While we are at it, actually, in your partition function, if you also, instead of just integrating over gauge field, if you also sum over these integers, that means you are moving to SUN mod ZN theory. You are gauging the symmetry and you are moving to SUN mod ZN theory. But we will always stick during this class in SUN theory. And we will consider this SUN theory with these interesting backgrounds. And that will help us to figure out some interesting things. So, but this is the relation between SUN and SUN mod ZN. Now, as I said, so you can choose these transition functions to be completely independent of the space. That is one choice. If you look to Polyakov loop, in the presence of this 't Hooft flux background, its proper definition is actually gxy exponential I 0 to Lx, Ax, x, y, dx. Now, actually, this is the usual Polyakov loop, and you know that it transforms as box under here, box bar under here, and the trace of it in the presence of this 't Hooft flux is not gauge invariant. To make it gauge invariant, to make this object transform as an adjoint, you attach this transition function, and this transition function, this is this holonomy part. The transition function transform as a box here and box bar here, so that this object here end up transforming as adjoint. Okay, and if you take the trace, it's gauge invariant. Now, in the okay, what does this mean? So if we, in the presence of this Wilson loop, the fact that okay. Give me a second. How should I say that? This thing, the Polyakov loop, Px, turns out to be completely determined. I chose I chose my things opposite. So according, you know, with respect to my convention here, this part can be set to be 0. When you make this transition function independent of space-time, you can actually show that you can set the gauge fields to 0 exactly. Okay, then that tells you that the Polyakov loop in the x direction can be shift, and Polyakov loop in the y direction can be clock. These are not simultaneously diagonalizable, but it also tells you that if you look to any combination, trace P3 to the power N3, 3, 4, X, Y are same thing, okay? So it doesn't matter. And 4, this is equal 0 as long as N3, N4 not equal to 0 mod N, okay? That means that with the insertion of these to Hooft flux, you can actually preserve these Zn 0 times Zn 0 part centers of the center symmetry. You can keep the symmetry that was broken in the absence of the flux intact. So the system is as if you have two adjoint X fields. If there are any people here familiar with, it appeared yesterday a lot, N equal 4 super Yang-Mills theory. There is a well-known deformation of it called beta deformation. This is, if you happen to know that, this is identical to that. There you have, for example, commutator of two scalars, call them phi 3 and phi 4, and in the potential, and you can put a phase in this commutator, and that makes the ground state structure just like this. So, but what does it do? If we take, for example, the combination of these two, actually does something very dramatic to the gauge field. So let me move this forward. Okay. Even if you start with SUN gauge field, now you have these Polyakov loops. One of them is clock, the other one is shift. And the only thing that will commute with both is identity metric. This actually breaks SUN gauge group down to Zn. So the only elements of SUN that commute with this P3 and P4 are proportional to identity, and they can only take Zn values. And as a result, everything in the spectrum is gapped. Now, things get interesting. If everything is gapped, what will happen? This is, okay. And let me tell you how things are gapped. So let me show you perturbative mass spectrum. So we are using, okay, we are using some gauge fields, x comma x3 plus L, let me take it symmetric, x4 is equal to S inverse A x comma x3 x4 S. These are, again, I am writing my twisted boundary conditions, x3 x4 clock inverse A x3 x4 clock. This is twisted boundary condition of the Hoofts. This is how we implemented to flux. Now, actually, you can use these clock and shift matrices. This is something quite pretty, honestly, but you have to do it on your own. For the n by n matrices, general n by n matrices, you can construct a basis just on clock and shift. So you can construct the following basis: J sub P, that we call, and P will be a 3 vector, a 2 vector P3 P4. Okay. Clock to the power minus P3, shift to the power minus P4, omega minus, this is for convenience, P4 divided by 2. So this is a two-component vector, and J sub P dagger is J minus P. And what you can do is, you can, this is an n by n matrix. It is a traceless n by n matrix. Oh yeah, thank you. Thank you. Good. These are n by n matrices. You can actually decompose them as follows. X, X3, X4, it doesn't matter, these labels. Sum over P not equal to 0, JP, AP. Actually, you can write n by n matrix in this basis. It's n by n matrix, but it has n square minus 1 degree of freedom living in it because it is traceless. So I made a sum over all P, not including the origin, not including P equals 0, 0. So I expressed my n by n matrix by using this basis. Okay. Now, these modes, these P3 and P4, they will become, oops, this is heavy. Okay. Okay, what do we do now? Let's bring down. Let's bring down this. Okay, where is this part? So in terms of this, the twisted boundary condition, in terms of these A sub P amounts to the following: A, P, X, X3 plus L, X4 comes out to be omega to the P3, AP. And similarly, if you do it for similarly for the other components, okay? So, okay, then you can decompose this mode. This is like Fourier decomposition, X, X3, X4. This is, after this step, the perturbative spectrum will be transparent. There is a sum over K3, K4, over all integers, A, whatever component we are interested in, P, K, exponential 2 pi I divided by NL, N K3 plus P3 times X3 plus, this will be the punchline of the spectrum, NK4 plus P4 X4. You can decompose the field in this manner, P component of the field in this manner. So these are the momentum modes, and this will tell you that the mass square for the P comma K components, okay, will be 2 pi over NL square, NK3 plus P3 squared, NK4 plus P4 square. This is the perturbative spectrum. It tells you that every mode of the gauge field or whatever adjoint matter you have in the system is completely gapped. Everything is gapped. And if you really want to, if you really want to look at this picture, normally if you do normal compactification, the modes will be quantized in, again, 2 pi over L, comma 0, 0, 2 pi over L. And in the normal compactification, the Kaluza-Klein modes will be compactified like that, and each one of them will have n square, order n square degree of freedom. But with the spectrum, what's happening is that this n square, it just degree of freedom breaks up, and it generates a much finer mesh, much closer, finer mesh, where this becomes the perturbative spectrum. And again, this is perturbatively, this is spectrum. Everything is happening within here compared to that picture. All the degrees of freedom acquire a mass from compactification, but there is no zero mode. The important thing is nothing here. Yet here we had two-dimensional gauge field, which was an n square component matrix. And so this is the consequence of the perturbative analysis. And the fact that even at fixed L, as you take n infinity, this spectrum becomes continuous. It is related to, again, large n volume independence, something called twisted Eguchi-Kawai model in retrospect. Okay. So perturbatively, the story seems quite boring. You had an SUN gauge theory. It is broken down to Zn, and everything is gapped out. And perturbatively, this is actually end of the story. Okay. But at least this thing tells us that Zn cross Zn is preserved. Okay. So question is, what happens non-perturbatively? Okay. So to answer this question, let me now discuss a little bit the 2-Hooft flux and turning on all possible cycles on the 4 torus, and we will do something interesting with it. And perturbatively, actually, maybe I should write this down. There is one form symmetry, zero form, and because everything is gapped out, it looks like there is no long-range field. This is broken down to 0. So perturbatively, this one form is broken. But this is now very similar to Polyakov model. Remember, in the Polyakov model, to all orders in perturbation theory, you had gapless photons, and you did not have confinement, at least linear confinement. And in that sense, one form symmetry was broken as well. But there were these non-perturbative objects, monopoles, and they did something very interesting. And we will encounter something very similar here, something quite interesting. So let me take my M2 to be T2. Let's consider the theory on T2 times T2. I will take this T2 to be small, smaller than strong scale. This T2 to be long, larger than strong scale. As I said, on T4, I have these Zn one form symmetry. And to capture it, I can introduce, to capture the one form symmetry, I can introduce a two form background and B2, a two form field. And These two-form fields is related to the two flux as follows. We can introduce these two Hooft fluxes in mu nu. This is equal to the integral of this two-form field. It's a Zn valued two-form field. Integral of these two-form fields over T2 on mu nu. These two-form fields is actually nothing but the two Hooft flux, discrete two Hooft flux. When you integrate over these two-form fields, also in your PET integral, you will go to PSUN theory. But as I said here, we will always stay in the SUN theory, but we will turn on these two-form field backgrounds, which amounts to Hooft flux. Now, an old observation due to Hooft, Van Baal, and many others, and which also comes in the newer literature on the subject. Oh, I can make a little bit more use of this. The definition of the topological charge changes in the presence of these two-form fields. So the precise description, quite precise description, is given in the works of Nati and his collaborators. But topological charge, which I have written down there, FHF, this was for SUN. The precise machinery to do this requires you first to go to UN. Actually, this two-form field is realized by introducing a pair of one-form and two-form field, by introducing something like that. That first requires you to go from SUN to UN. But the topological charge is modified as follows. Topological charge 1 over 8 pi square, integral trace F tilde. F tilde is now UN field minus B squared. This is equal to 1 over 8 pi square, integral trace F tilde square. This part is an integer. And the rest becomes minus, 1 over 8 pi square, integral and B square. And this part comes out to be, if you calculate this data will be given to you in terms of these n mu nus. And the way it comes about is following. This comes about to be topological charge. This is important. Topological charge happens to be minus 1 over n, epsilon mu nu rho sigma n mu nu n rho sigma divided by 8 plus z. This is something interesting. In the presence of these background flux, okay, the topological charge is no longer quantized in integer units, but it is quantized in units of 1 over n. Okay. Is that clear? Now, okay, let me push this up first. Okay.
Column, that's block matrix, right? It's 0 along the back.
Yes.
So my conclusion is that is not full length. So it seems like
No, it is.
there's ones below.
There is a one below there. Actually, if you diagonal, you can find a unitary transformation to diagonalize that S, and that will give you the clock matrix. The eigenvalues of both of them are roots of unity. This is the reason, the Zn cross Zn symmetry, center symmetry is intact throughout the analysis. Yeah,
Thanks. Great.
yeah, yeah.
Yeah, yeah, right. Okay, second question. So the reason we had no massless modes, it seems because of the t not equal to 0 in the sum of x, x4, j,
Yeah.
somewhat t not equal to 0, j, t, a, t. So it seems like that sum t not equal to 0 is doing a lot of work. I didn't exactly track where that came from. Say it one more time.
Oh, actually, this A gauge field is an n by n matrix, but it is a traceless matrix. So it has n square minus 1 entries in the n square minus 1 independent components. This J sub P, the way I constructed it, is a basis for n square for n by n for traceless n by n matrices. This is a quite beautiful basis, but I won't say much about that. Yeah.
But I also maybe say the n p3 equals n, p4 equals n, the same as.
Yeah, yeah. Yeah. Now, actually, this sounds very nice. It tells you that topological charge is quantized in units of 1 over n. And one may naturally expect that, you know, if there is a configuration satisfying BPS bound, okay, the Yang-Mills action will be, you know, 8 pi square divided by G square Q topological. And if there is 8 pi square divided by G square n, it's instanton over n. And you see the same combination also appears here from our earlier analysis, but for completely different reasons. Okay. However, the problem here is following. Although I didn't detail it very much, in the previous lecture, you had this BPS equation for the monopoles, and the solutions are not difficult. You can find them. Here, the solutions are actually extremely difficult to find. There is only one relatively simple solution found by 't Hooft himself. And, you know, at least there is a solution, but it is like a solution which is constant throughout the space. Yet for the instanton, we expect the instanton to be some lump somewhere, okay? But on the lattice, people worked a lot on this, on the lattice field theory over the last 20, 30 years, especially Tony Gonzalez Arroyo and his student Margarita Perez. And they found localized fractional 1 over n configuration exactly using this setup, okay? So we will put some faith on it and assume that non-trivial local solution exists. This is the only assumption we are making at this stage, okay? Now, here comes very interesting part of the story. If you put one of these solutions classically, let's take you take a solution. Let's take you have a Wilson loop in some representation R, okay? And classically, you look at the Wilson loop, what it does. The Wilson loop comes out to be the following. The Wilson loop is equal to 1 if the solution is outside. Let me call this vortex 1 if V is not inside C. But if this vortex is inside, it is exponential 2 pi I divided by n. And let me call anality of representation R with magnitude of R. I know it's not a great, great naming, but so if the vortex is inside, it gives you a phase, okay, for the classical Wilson loop. If it is outside, it gives you nothing. This is actually, this vortex is an anality, the meaning of anality. So it is number of boxes in Young tableau modulo n for representation R, okay? Take some generic representation, count the boxes in the, we can count, you know, and make it mod n, that's the anality of the representation, okay? Now, that's very good. And this object here is actually the thing that we call, that's called center vortex, is actually is generator of the one form symmetry. So its relation with the Wilson loop is as such. It only depends, so it essentially determines the charge of the Wilson loop, okay? And you can really think of this object as, yeah, generator of this one form symmetry. Now, there is this object. We assume that it exists, you know, it can be localized, and we can do something. Now, I will use only middle word now because now I will do something very concrete. But let me actually start from here and make my way. But okay, the fact that everything is gapped may sound like it may be hopeless to have confinement and things like that. But there is something called abelian X model in 2 dimensions. It's a fairly nice model. It also it's a U1 gauge theory with some scalar. It also goes the same fate. Everything is gapped out perturbatively, but you can show that there are vortices, and the proliferation of these vortices do some very interesting things. So now these vortices are of finite size. We can think of a dilute gas approximation, okay? Dilute gas. This is a controlled approximation now, approximation. This is controlled. Let us take again, I took M4 to be T2 times T2. So let me do the following, okay? So let me take, okay, M2 can be large, okay? M2 times T2. This is where I inserted flux, N3, 4. Let me put 1 unit of flux only there. And let me not bother about inserting any flux here. N1, 2, all others, M1, 2, and the rest are all 0, let's say. And there are these objects here, these vortices and anti-vortices filling up the space. They are of finite density. Now, I have chosen my 2 hoof flux such that here it's becoming more interesting. Look, if you look at the topological charge, the 1 over n part will be proportional to the product of n1, 2, and 3, 4. But I have chosen n3, 4 to be 0. So the topological charge, whatever configuration I take, I sum over, must be integer. Despite that, something very interesting will happen. So if I take some configuration with n vortices and n bar anti-vortices, let's say n v's and n bar v bars anti-vortices, the topological charge of that configuration will be n minus n bar divided by capital N. And I will denote the vortex here as some prefactor, which is not very important for me, is instanton divided by n plus I theta divided by n. This is my vortex operator. Now, let us construct the partition function. This is probably the most interesting thing that we will do related to this. Okay, z of theta. We can sum over all vortices, all anti-vortices, right? This is a grand canonical ensemble. And I decided to write down this explicitly. Let me call the volume of this space, volume of M2 to the power m plus m bar divided by m factorial, m bar factorial, k to the m plus m bar, exponential minus n plus n bar is instanton divided by n. But for the topological charge, I theta over n, n minus n bar, okay? But because of this condition, because of the fact that I set M12 to be 0, I must only sum over integer topological charge configurations. How can I do that? I can put a Kronecker delta here. N minus n bar must be capital N Z. If I do that, the topological charge will be integer, okay? To find the partition function, I need to do this sum in the dilute gas approximation. Because I chose N34 to be 1 and N12 to be 0. That tells me that topological charge must be integer. And I am taking some M2, either compact manifold or whatever you would like to choose. I have to do a sum over integer topological charge configuration, but a generic configuration, including n vortices and n bar anti-vortices, have this topological charge. If I want to sum over configuration only with integer topological charge, I need to put this. This guarantees that I am only summing over integer topological charge. But the interesting thing here is that the object that enters to the sum may very well have fractional topological charge. But for example, if you have a vortex here, V, with topological charge 1 over n, and another one there, minus 1 over n, anti-vortex with minus 1 over n, that enters to the sum. Okay, that is the difference from not considering any vortex at all. Now, for this thing, there is a Poisson, there is a formula you can use discrete Fourier transform. Oh, 0 to n minus 1, exponential minus 2 pi I k. Some very interesting things will happen. Pay attention, okay? This part. N bar, okay? I just wrote this Kronecker delta, you know, by using the Fourier transform. Okay. Now, let me do this. If everybody wrote this formula, I will be a little bit lazy in writing. Yes. Yeah, for normalization. Yeah. Okay. I will erase this, okay, because I want to use the above formula. I will modify the above formula, sum over k. I will replace this thing with this face. Okay, it goes, here it goes. I will also erase this. Now something interesting happened, okay? Let me rewrite this part. Something interesting happened. The interesting thing is I theta minus 2 pi k divided by n times little n, I minus I theta minus 2 pi k divided by n bar. What happened now? The sum over n and n bar, which were a constraint sum, now become unconstrained. I can do it because I know how to expand exponential of x to a power series, and the thing that is written down there is that. So this is equal to sum over k equals 0 to n minus 1 exponential minus volume of this M2 minus 2k exponential minus s instanton divided by n cosine theta minus 2 pi k divided by n. And we obtain exactly the same multi-branch structure as we did earlier. But the objects that we base our analysis on are these objects which have non-trivial mutual statistics with the Wilson loops. They are genuinely different from monopoles. The usual our monopoles were in the root lattice. They do not have non-trivial mutual statistics with the Wilson loop, okay? Now we obtain this multi-branch structure, and this part is nothing but energy of the branch K as a function of theta. And if I write it in terms of strong scale, it is minus lambda square lambda L small to the power 5/3, and this cosine theta minus 2 pi k divided by n. Now, I don't have plenty of time, but now I want to show you what happens. This is the partition function. What happens when you put a Wilson loop, how this sum to get modified, and what should we think about, etc., etc. And it is again something elegant. So let me put maybe let's keep that there. Let me modify a little bit this picture. Okay. Let's say this is my M2. It doesn't matter what it is. Let me put a Wilson loop in representation, Wilson loop in representation R. Now, I want to calculate expectation value of the Wilson loop. So I have to put this thing into my pet integral and do corresponding sum. So how do I do that to calculate the Wilson loop? Let me take advantage of some things. Okay, let me tell you first what I want to tell you. Here is the thing. We will do the same sum again, okay? But I have to distinguish, let me call this area A, and let me call the complement, this part, V minus V of M2 minus A. This is the complement. I will call vortices inside A. Let's say there are M1 vortices inside A, and M2 vortices in V of M2 minus A, and 1 bar also is in A, anti-vortices in A, and 2 bar is in the complement minus A. So now my vortices fit into two categories, those which are inside of the Wilson loop and those which are outside. What is the difference between them? Can somebody tell? In the sum, what will be the difference between them? The phase. The ones inside the Wilson loop will pick up an extra phase depending on anality of the representation. Okay, I will still do the same sum, but the ones inside will do some interesting things. Okay, and one, okay. So if you are inside, if you have this vortex here, it will have this exponential I theta over n, but it will also have I 2 pi over n representation R. Okay. Now this is interesting because now I can go ahead and calculate Wilson loop in representation R. Expectation value in this grand canonical ensemble. There is 1 over z of theta. Now I need to do sum over n1, n2, n1 bar, n2 bar. Okay. There will be n1 factorial, n1 bar factorial, n2 factorial, n2 bar factorial, and here n1 plus n2 plus n1 bar plus n2 bar. Let me put everything here, k exponential minus s instanton divided by n, everything in there. Okay, I am still doing the same sum. Okay. Now the phase factors will be different. This is the important part. If it is inside m1 minus m1 bar, we'll multiply theta over n plus 2 pi over n, something related to representation. If you are outside I, n2 minus n2 bar, theta over n. But this is not the whole story. I am forgetting something. I didn't put my constraint yet, right? I must have m1 plus n2 minus m1 bar minus n2 bar must be an integer because I am doing a sum over integer topological charge configurations. Yes.
So I'm confusing a couple of Ks. I'm trying to remember earlier, one of the Ks is related to the thing that appears with the topological charge and is not related to the
This capital K is fractional instanton prefactor.
Thanks. So there's a sum over K.
I am sorry. I messed up. I didn't yet put that sum because I need to do only a sum over, thank you very much. This is important. There is no K there. And there is this thing. Now actually I will make some, okay. Now I can use that little K. Again, thanks for this question for clarification there. I can now actually use the same Dirac delta to convert this sum, to convert this into a sum over K. So I am erasing this one, putting a sum over K there, okay, and putting these appropriate I 2 pi over n k n1 plus n2 minus n1 bar minus n2 bar. And you can do this sum. You can do this summation. It's not very difficult. And here is what you obtain. You obtain 1 over partition function as a function of theta, sum over k equals 0 to infinity exponential volume ek of theta. Now comes the interesting part, minus area ek. If it is inside, theta is shifted by the representation. Minus ek theta. Okay. This is the result of the calculation. Okay. So let us restrict theta angle to be between pi and minus pi. In that case, k equals 0 is the vacuum. Okay. And we want to take volume goes to infinity limits. Volume goes to infinity limit in this construction. We keep the Wilson loop fixed there and take the volume to infinity. And you can immediately see that R of C becomes exponential minus area E0 theta plus 2 pi R anality of representation minus E0 of theta. Okay. This is the area of confinement in this case. And this is your string tension for representation R. As a function of theta. Actually, you should appreciate that something very interesting happened. First of all, the tension came out to be just only dependent on the representation. Okay, on the anality of the representation, not representation, anality of the representation. Okay, this is important. It is sourced by different objects. And when we were doing, for example, confinement based on the monopoles, the string tension really depends on the charges of the external probes representation within at least effective field theory that you construct, because if you forget the W bosons. The fact, you know, this thing is quite interesting in certain regards. Now, this is more or less all I want to say. This is the derivation of the confinement on this R2 times T2. The important thing is mechanism is due to these center vortices. And I must also say a few more words. In the lattice community for a very long time, people worked on these center vortices, especially Jeff Greenside and his collaborators. And they have ample evidence from numerical lattice simulations. But one of the problems there for over long periods of time is that they did not have any semi-classical theory that they could rely on. They did not even have a regime, but there seemed to be lots of evidence in favor of something like this. But now, in my opinion, the situation is more interesting. We now, at least with 2 Hooft flux background on R2 times T2, we can show semi-classically that the center vortices generate confinement. But on R3 cross S1, it was the monopoles. Both of them have fractional topological charge 1 over n. But they are genuinely different things. They have different mutual statistics with the Wilson loops. It tells you that something more interesting is going on here. Okay, it is not, and it's an open problem to understand what is really happening precisely here. There are other ways, there may be some hints about it. There are other ways to implement 2 Hooft flux. Here, I implemented 2 Hooft flux by using a flat connection, by forcing F3-4 to be 0. Actually, there are, if you use a 2 Hooft construction, but instead of using clock and shift, if you insist using, for example, in some abelianizing gauge theories like Seiberg-Witten or Polyakov or Deform-Yang-Mills, if you insist on using abelianized transition functions, it forces you to put some genuine background magnetic field. You cannot use background flux. It's not a flat connection. You have to use genuine background magnetic fields, and you can achieve 2 Hooft flux again. And that may provide a hint between these two, because you start with some abelianizing picture, but it's an open problem. Okay. I prepared actually 3 things, and this actually gave me also a perspective, because I prepared Yang-Mills, then I was going to super Yang-Mills, and I was going to go to QCD with fundamental. And I decided to stick only one of the topics at the end. I am on page 7 of my 15-page notes, okay? But it is good, at least you engaged. I can just make some minor comments. If you do the whole thing with in n equal 1 super Yang Mills, you do get chiral condensate correctly. Okay, and it is extremely similar. The reason not to write this down is justified because it's extremely similar to what Witten did in his classic paper where he calculated the supersymmetric index by using 2 flux. There is a section like that. It is relatively hard to penetrate, but yet it is one of the clearest thing written till that. The most interesting thing I wanted to tell, I couldn't tell for the sake of making this exposition clear. QCD with fundamental. I just want to tell you 2 things. One of them, when you have QCD with fundamental, you do not have one-form symmetry. Quarks have charge under one-form symmetry, and you cannot impose twisted boundary condition. But here is the thing. The theory has a U1 baryon symmetry. And under that U1 baryon symmetry, remember that quarks have fractional charge, baryon have integer charge. And this is a work I did fairly recently with Yuya Tanizaki from Yukawa Institute in Kyoto. You can actually turn on a magnetic flux background for that U1 baryon symmetry. Just a background. But then, here's the super interesting thing. It allows you to have twisted boundary condition by using the structure group SUN times U1 mod ZN, okay? So you can actually, even with QCD with fundamental fermion, with any number of flavors, you can, in principle, put the 2 flux. And this was my, one of the things that I got shocked most, because on large T2, you know, in QCD, you expect chiral symmetry breaking and a chiral Lagrangian, and turning on this background is equivalent to coupling this background to skyrmion current, baryon number current, and that gives you chiral Lagrangian plus a skyrmion term. Compactify that naturally lives in some 5-dimensional auxiliary space, but compactify that to M3 times R2, M3 times T2, okay? And use this 2 flux, it reduces to SUN WZW, Wessumino-Witten theory in 2 dimensions. If you study this kind of theory on arbitrarily small T2, you show that Dirac operator in the background of this magnetic flux background has n 2-dimensional Dirac fermion 0 modes, and you can do non-abelian bosonization, and it gives you UN level 1 Wessumino-Witten. You get then also center vortex helps a little bit, and you do get SUN level 1 Wessumino-Witten. So long story short, the theory that you obtain at arbitrarily large T2 is equivalent to the theory you obtain at arbitrarily small T2. It is SUN level 1 WZW. I think that was the thing that I was surprised most, but it is a little bit more advanced, but it is understandable still. Let me stop here. I hope this lecture was more pedagogical and better. So.
For very inspiring lectures. Just a quick question about this. The last thing you said, those are CFTs, right? Yeah.
They don't CFTs.
Yeah. So they won't have gas.
Yeah. They flow to CFTs. Actually, naively, actually, if you take chiral Lagrangian and compactify it on R2 times T2, just look to 0 mode, it reduces in 2 dimension to some nonlinear sigma model called principal chiral model. And the theory is very well known to have a mass cap. and unique vacuum. But when you couple it to this Skyrmion current, you know, it flows to WZW CFT. And yeah, and the same thing is satisfied by non-abelian bosonization of the fermions.
So the center vortex, sort of by definition, only sees the anality of the Wilson loop.
Yes, exactly. This is the reason it gets the representation dependence based on anality, right?
Objects that are also representation dependent. Evidence, right, for the center.
Right. The answer is yes. you are asking if there are other objects which can probe representation rather than analysis. Yes, the answer is yes. I mean, but these are the things related to something called non-invertible symmetry. For example, in certain cases, for example, if you take two-dimensional pure Yang Mills, it also has a ZN center symmetry, but this model is solved. It is almost topological because it doesn't have propagating degree of freedom, and it is solved. There is no problem there, and tensions are representation dependent. This is also exact. But the explanation of this fact in terms of symmetries is that there is a non-invertible symmetry which is generated something very similar to Bukov-Witten operator. I constructed another model on R3 with, again, Yuya and Mendel, and that was very similar in essence to Polyakov model. It's you want the n-1 gauge theory with semi-Dirac with Sn. Hence, it is really non-abelian, but the dynamics is abelian because Sn is topological, yet it's part of the gauge structure. In that case, we constructed operators in this theory, which explains the representation dependence of the string tension. The string tension comes out to be representation dependent rather than anality dependent.
Okay, I think coffee break is calling us. So thank